This is thermoplastic polyurethane, or TPU. This is Charlotte. This finding seems obvious in hindsight, but I'm nonetheless thankful that I noticed this quirk of gate design. And as you can see, what effectively this does is just move the foot link, which is this guy here, just up and down. Floppy leg, I guess you could call it, mounted onto Charlotte. With no load, we were getting 50 milliamps. Here we're getting, seems like between 8 and 10 milliamps. You can see there's a point where it just buckles.
In medicine from 1923, it went for the discovery of insulin.
Welcome back. Hopefully, I've made my 2-week deadline to get this video out. If I have, please say you're proud of me in the comments below. Last time, I demonstrated how flexures could be used to create a scalable spider leg mechanism with specifically coupled degrees of freedom. But the amount of current that was needed to drive the leg was high, very high, even without any external load. The flexure's innate stiffness was causing significant problems, so much so that an entire robot with 8 legs was completely infeasible. Let's flash back to 2021, when I was busy inventing what would become a glove that could trigger any wearable device. Eventually, I came up with an electronic sensor. But I initially wanted to keep the system mechanical, which meant I foolishly committed myself to building a logical mechanism. I needed this mechanism to be small, so I wanted to avoid the tedious assembly of multiple pin joints. It would be great to have large parts of the mechanism completed in just a few 3D prints. If you watched the first video having to do with this project 2 weeks ago, you know this means I used flexure mechanisms. I turned to multi-material printing so that rigid TPU forms the links, while soft TPU forms the joints. And this worked wonderfully. Even then, I knew this would be a powerful technique for future projects. And now I'm confident this same methodology will let Charlotte run before she can walk. This video is sponsored by Dragline Dynamics. Are you a cosplayer or a real-life superhero? Does your supersuit need some transformative technology? Protect your secret identity with Symbolite, a flexible lighting fixture that can hide under any garment. Order now at www.dragline.tech. Or, if you want superpowers for real, consult our expert who has graduate degrees in engineering and a decade of research experience. Schedule today at www.dragline.tech. Dragline Dynamics is democratizing technology for modern heroes, and that means you. There are a few things to address before we get started. First, I had a lot of comments remind me of rolling contact flexures. Now, I'm not going to pretend I knew what these were called before I posted the last video, but as someone obsessed with mechanisms and whose Instagram feed looks like this, when I Google rolling contact flexures, my response is essentially, oh yeah, those ones. Now, I have seen these before, and they are really cool, but I have some things I'd like to clear up about them after some research. This video, by the channel Breaking Taps, demonstrates rolling contact joints in another tiny robot design, which, interestingly enough, uses tendons to drive the joints. I guess sometimes great minds think differently. In their design, tendons were also used as the flexible part of the rolling contact joint, the part of the joint I've seen referred to as straps. So if you hear me say straps, that's what I'm talking about. One curiosity I have is not so much about the joints themselves, but more so the discourse that pertains to them. I've seen at least a few claims that this is how joints in the human body work. This video does so as well, and it specifically uses an image of a knee to illustrate this. The knee in particular does seem to be a common comparison case. I even asked you guys on YouTube and on my Instagram at the.amazing.labs, which joint in the human body works like this? 240 Cores said, knee? Internet Observer 007 responded with this GIF. And Castle Renee said, this. What does this mean? Now, I don't want to say flat out that this comparison between rolling contact joints and the human knee isn't valid. It's not exactly the most debunk-worthy claim on the internet today, but it provides an opportunity to spread some knowledge nonetheless. It is valid in the sense that you have two ligaments, the straps, like the ACL and the PCL, holding two rigid bodies together as they are constrained in their relative movement by tension and compression. Now, what the knee largely relies on that is absent by definition in the rolling contact joint is, well, sliding contact. And that's right. In fact, all of the synovial joints in the human body rely heavily on surfaces that slide against one another. I thought I would share that little tidbit. I would love to talk more about the knee because it's an absolutely fascinating joint. It's not a true hinge joint, it's a Chebyshev linkage. Why isn't it a rolling contact joint? How the tiny ACL and PCL are extremely important. Ultimately, I'll get into it if there's ever a video where that stuff is a bit more relevant, but I encourage you to research a bit of the biomechanics yourself. It's all lovely science. I was still unsure if these rolling contact joints could help at all with Charlotte's development, but I was more than willing to investigate. All right, so here's my rolling contact joint printed with PLA. And because it's PLA and not one of those flexible TPU materials, it has bending stiffness. So you can see this basically consists of two halves here, and we have these straps that sort of wrap one way around here, and on the other side, it runs the other way. And what that means is, regardless of how this is bent, it's constrained to be these two halves pulled towards each other by the straps. As you can see in the video from Breaking Taps, you can also construct these by just tying strings to act as the straps, having tendon straps basically. That is pretty labor intensive, and I was trying to avoid that for Charlotte. As a result, I was able to make a print in place version. So this is a single part rolling contact joint with bending stiffness. So here we have another variant of the rolling contact joint, and this one has much less bending stiffness. It doesn't really resist me as I push it, and you can see it can bend very far suddenly. This one is made out of TPU. We have the hard TPU making up the frame here, and the soft TPU making up the straps. So this is pretty cool, but it's the same shape as the other one, just a different material. And you can see what happens if we twist. It does not resist that at all. You can see the straps completely unwind. And so that's one thing that the PLA version has against this, is that this is able to deform pretty heavily in an unintended direction. Now you could have like multiple layers of this. That gets pretty difficult to remove the support material. It's really, really cool, but it needs to be constrained along the plane. That's something that my existing flexures don't really need, which is nice. I tried to shrink this down and make it smaller, but the support material got really difficult to remove, and I can already see in some places it's welded in such a way that it really should not be. So you require quite high tolerances to keep the straps separated from the wall here. Since TPU is a lot less brittle than PLA, it becomes harder to remove the support material. It sticks to itself really, really well. Thoughts on making these smaller? I was gonna go the whole distance and see if I could make a leg with these rolling contact joints. But as cool as these are, I don't think they're gonna be the right approach for the leg. They just don't have the scalability that I require. But still very cool, and they might end up being useful for something else. It's a super fun fidget toy, that's for sure. So as you can see, the rolling contact joint has a lot of promise, but it lacks the scalability of the types of flexures that I showed previously. Some other comments brought up using stiffer materials to counter the unintended degrees of freedom. I just want to say this would counter the desired degrees of freedom as well, as shown in my last video when I tested a stiff leg. The motor stalled out, and our goal here is lower power consumption as much as possible. As a reminder, this goal is currently taking the form of minimizing the current draw while driving the leg at 5 volts. So finally, let's get to the meat of the video. Last time, we ended up testing a leg made of the softest TPU, having a shore hardness of 85A. This leg exhibited a pretty much desirable current draw of about 80 milliamps, just 30 milliamps more than the mechanism without the leg attached. The problem was, this leg is compliant to the point where it completely buckles under a very modest load. Not exactly something you want your personal robot to do. So this multi-material technique I talked about in the intro instantly sprang to mind. It was a Jimmy Neutron brain blast from the past. Here's the general idea. You design a flexure mechanism with joints and links as shown previously, but this time, in the direction perpendicular to the motion plane, you either thicken the links or thin the joints. Then, when it's time to print, you add a material change from soft to hard TPU as soon as just links are being printed. Now let's talk about why both materials should be TPU here. A lot of people brought up PETG and PLA for hard materials, and while I've only tested PLA as an alternative, we have to consider the miscibility of the soft and hard polymers in this case. That is, can they be mixed without a preference to separate? TPU is TPU, polyurethane is polyurethane. A substance is always going to mix well with itself. PLA, I've found, separates very easily from TPU for one reason or another. During the high temperature welding of two polymer layers, like in 3D printing, some diffusion needs to happen between the layers for sufficient adhesion to occur across the boundary. Initially, the huge tangled bundle of polymer chains in each layer are separate from one another. When the layers are deposited, it's not like you're forming new covalent bonds between the chains. If that were the case, 3D prints would be far stronger. Here's what happens. Each side of the boundary's got a bundle of polymers, right? At high temperatures, the polymer chains become much more mobile. They can slip and slide past one another, effectively forming the macroscopic liquid or paste-like substance that we see. This allows for a process called reptation, Taylor's version, where the chains from each side of the layer boundary snake themselves into the other side's bundle of chains. Then, once the temperature cools and the chains become less mobile, the layers are locked together. Now, I can't say for sure why PLA and TPU aren't able to diffuse super well into each other, but they have a very different molecular structure, so that could have something to do with it. As I said though, we can be certain that TPU is miscible with itself, so we should expect good layer adhesion as a result. So when we print this leg with both soft and hard TPU, we can expect that the leg won't fall apart. Let's take a look at the legs I've made with this method. So looking back at the legs we had last week, we had the medium stiffness TPU leg. That's what we started with. Then I just took that same design and built it in the soft TPU. This is clearly not built for the hard skeletal structure that we need. So if we take the technique that I showed you guys, we end up with this. These bottom layers are printed in the soft TPU, top layers in the hard TPU. You can see the joints are left as the soft TPU completely. It's very flexible, and yet these pieces are stiff. The only issue is, you can see I'm really fond of this like wedge design here, where the tip of the leg comes to a point and the opposite faces are angled towards each other. And as a result, I don't end up with a full top layer for this link of hard TPU. And so we still have this softness here, which is not great. Additionally, it seems like keeping these joints long it's not going to really work because we have extreme flexibility in unintended directions, which is not good. So I think more work needs to be done on this one, but this is just the basic idea of taking my layered multi-material approach and applying it to this leg design. All right, and here we have that first hybrid leg prototype mounted on Charlotte's body with the motor running. And it looks like we're getting about maximum 0.1 amps, 100 milliamp. Very similar to what the purely soft TPU leg was giving us. That makes sense because this is still mostly soft TPU, but the issue is it buckles extremely easily. Really doesn't resist at all. So I wouldn't expect this to be able to walk pretty much at all. So next in leg evolution, I came up with this. And to get rid of that like extreme bending problem here, I just blew up the links, basically made the joints smaller. And to stop the fact that this, only has hard TPU on one side, this is bending a lot here, I actually modified the technique somewhat so that I actually do a whole few layers of hard TPU and then soft, and then more layers on top. So the joint is only found in between here and here. And this design certainly has some stiffness to it. Also still bends in unwanted directions, but I'm going to attach it to Charlotte's body and see how it performs. So here we've attached that small jointed leg here. And you can see, looks pretty good. But we are experiencing some more current. We're getting as much as 0.17 amps. So we're approaching again, you know, the draw that was required for the medium stiffness TPU, and that's obviously not what we want with this approach. If I try to make this collapse, also collapses pretty easily on that side as well. I could see possibly walking being done on this, but still, I do believe that there's a way to improve this design even further. Oh, hey there. I'm just over here giving Charlotte a hip replacement. I just wanted to let you know, this is currently the second video I've posted on the bi-weekly Friday 5 p.m. schedule, which is tricky since I'm actively working on my PhD. If you're watching this, there's a high probability you haven't seen some of my recent content. For instance, did you know I trusted my rappelling invention with my life? Did you know I post regularly on Instagram at the.amazing.labs? And did you know I'm working to miniaturize a super powerful and easy to use cable firing device? Check out all of that if you haven't already. And if you want to make sure I'm able to keep innovating within all of these avenues, support me with just $1 per month on Patreon at www.patreon.com/theamazing. Or if you can't support continuously, Dragline Dynamics is now accepting one-time donations via PayPal at the email draglinedynamics@gmail.com. You guys get to control how far my research is able to go. And remember, all you have to do to support the channel is subscribe. Now, back to the video. We're just inventing techniques right and left with this video. So here we have what I like to call, and I think I'm naming this for the first time, a socketed flexure. So we have that sandwich technique, and the flexure on the inside is made of the soft material, but the skeleton per se, the exoskeleton, just like a real spider, consists of these socket joints. They're like elbows. The bone fits right into the other bone, forms this coupling that only allows 1 degree of freedom. And this was my method of getting rid of those unwanted degrees of freedom. You can see it's not perfect. We're kind of losing material on this side due to the wedge profile, but I am interested to see how this does. It does feel like I haven't allowed for enough range of motion. This should get rid of most of those unwanted degrees of freedom that we were seeing before. I love watching this one move. All right, so here we have the movement of the socketed flexure. Looks very rigid. You can see that foot is staying completely vertical throughout the profile, and that's very good for the sort of not collapsing while walking. You can see this one can make it collapse still, but it resists it a lot more, and it can pop right back up. Yeah, you can see it's able to exert quite a bit of force against the ground, making itself pop up against my thumbs holding it down. However, during its operation, I do see peak at 0.15. It's not too bad. It's actually even better now. It was pulling 20 that I was seeing before. Yeah, I was seeing the 200 amp spike. Yeah, I do think this can be improved. You can see it's quite noisy in the current. We have this most proximal joint here is kind of long. I'm allowing for a lot of flexibility there. And you can see that is kind of the cause of some of this unintended bending. And so I bet I can just make that smaller without sacrificing a lot of flexibility. You can also see that this is kind of, you can see it's kind of being yanked here. Like it's pulling on it, I think. Yeah, because see, this is the resting point. And yeah, this needs to be pulled back quite a ways. Up here, this joint is already at its limit. at this spot. That's easy to fix with a different design, but that's an indication that this design is not quite right just yet. Okay, so I redesigned that socketed flexure here such that this most proximal joint is quite small, allows maybe for still some twisting here, but you know, not a whole lot. Yeah, I will say one thing I'm concerned about with these socketed flexures is this tiny joint up here. Don't think it's going to scale super well when, you know, eventually the design will shrink to resemble more closely a real spider. But regardless, I'm going to put this on Charlotte and see if it does better or worse than before. Okay, so we're seeing peaks at like 0.17, 0.16. So I do think the current could be lowered a little bit. Remember, when we have 8 of these legs, that's going to be multiplied by 8, you know. And yeah, so I'd really like to get rid of as much current as we can. However, it is much more resistant to buckling, which is good. And I think this one would definitely allow for walking. But the current is still just a little bit high. I want to see if there's yet still a way to make it better and make sure that there are no undue stresses on the mechanism while it's operating like this. With these 4 leg designs, I had a library of attributes to observe and learn from, and I spent a lot of time just watching them move to try to pick out their advantages and shortcomings. Okay, so our 2 phase 1 legs here did not work. Then we have these 4, which worked a little bit better in one of several different ways. This one had great current mileage, but simply is just too floppy to get the job done. This one, a little bit too stiff, but pretty supportive, but still not supportive enough. Then we get to the socketed versions, and we're seeing a lot of support, but still a little bit of high current draw. Let's get to the legs of the final phase of getting Charlotte to walk, starting with this one. So the first thing I add here is extra material on the side that doesn't go on the print bed. And like I said, I like this wedge profile here, but there's no reason why I can't add more material on top so that we actually do get some nice constraining socketed flexure joints here. That helped a little bit, I think, but you can see I'm starting to get a little bit spooked about degrees of freedom. You saw that one leg was kind of pulling out, kind of had a resting position that had this anchor pulling out of the socket of the body. And I got concerned that I was, you know, designing a flexure mechanism that was somewhat over constrained. That's the last thing that I want, because then I'm wasting current mileage for no reason. So you can see I kind of added the ability for this link between these 2 joints to be extendable and compressible, which is nice, but it adds a bunch of degrees of freedom that I don't think cause the leg to work properly. And then I got to thinking, and I'm like, okay, I added this crossbar to stop these from sort of rotating against each other, but clearly that doesn't really work. And the socketed joints on these guys actually do help with constraining the unwanted degrees of freedom. So I thought I'd turn towards that, but then learning from these guys again, you can see I did a little bit here too, I don't think all the joints need to be socketed. So I came up with this guy. And you can see I got rid of that crossbar. I didn't want to over constrain. I think the 4-bar linkage is enough. You know, I don't want to have too many joints for no reason. And the other thing I did was move the most proximal joint backward so that it's more inset into the wall and hopefully more aligned with the center of the nutation. So let's go ahead and try this one out. All right, so here we're looking at a really low current draw, peaking at like 0.1 amps, it looks like, or 0.11 at max, it looks like. And yeah, you can see it's working. The foot is staying pretty vertical. However, I will call attention to the fact that it looks like the top of that link, right? The part that's supposed to be this part up here is kind of facing us, which it should be facing upward like that. That is because I sacrificed one of the socketed joints here to be just a regular flexure joint, and as a result we are getting some twisting in that joint. I don't think it's harming the gait so much. You can see it does move the foot somewhat. I would just rather not have this able to happen because it adds undue stress on this flexure joint, and we're looking for longevity here. I think I'm going to add the socketed joint back in. So we're going back to having all socketed joints, but with this design, and then I think we're going to be pretty close. So I added that socket back in. We're seeing much better behavior by this top link here. It's not rotating so much. Foot is still staying completely vertical throughout the gait. And we're looking at about the same current draw as before. Can even get as low as 0.06, it looks like. So I think we have our winner for now. I want to get Charlotte walking. I don't think it's the perfect leg. It definitely still suffers from some of that unintended motion, but let's see if we can get it in its extended position. Yeah, in its extended position has a nice monostability. Doesn't buckle like the earlier version, just deforms and then returns readily to normal. With this leg, I think I'm ready to put the rest of Charlotte together and see if she can start walking on her own. That means it's time to make 7 more of these. Here she is. So I've got the motors hooked up, 4 motors, right? 2 for each side of the body. And I've got them hooked up such that the legs will work together to walk in approximately forward, you know. That means positive on one side is connected to negative on one side, negative to one side is connected to positive on the other side. Got them hooked up all in parallel. Let's see how much current we're drawing here. So remember, each leg before was drawing about 0.1 amps, meaning that altogether we should see maximum 0.8 amps. I'm hoping for a little bit lower. All right, so we're looking at less than half an amp. That's pretty good. About 0.45, 0.48, something like that. Yeah, you can see all 8 legs are moving together. Definitely a walking type motion, for sure. I love that. Look at that. That just looks so cool. Oh my goodness. We can also try to increase the voltage to increase the speed. 8 volts, 9 volts, and we're still looking at about the same current here. 11, 12. She's running now. Oh my goodness. And we're only looking at 0.5 amps. So that means that the current hasn't increased that much. And what that means is not a lot of the losses are attributable to viscous friction or velocity scaled friction in the mechanism, in the flexure. So that's good. All right, so now the question is, can it walk? Still got Charlotte connected to all her little wires, but I'm gonna go ahead and just run her and place her on the lab floor. She can definitely get moving, that's for sure. See, the legs are still kind of collapsing. She's still moving. Start turning up the speed here. Oh yeah. So you can definitely still walk, but she could get a great deal faster if those legs were a little bit more supportive still. So obviously control algorithms will come later. And I probably want to do a little bit more work on these legs. But I'm pretty happy with the fact that she can at least move. It's quite nice. Yeah. So in terms of like controls and steering and all that stuff, that will come. But this is looking pretty good. Definitely a good start. Yeah, and I think, you know, it's really heavy. Like, if I weigh this, like 180 grams or so, and yeah, I can basically half that if I'm able to do this with only 2 motors, which previously with the high torque flexure mechanism, I wasn't able to, but now maybe I am. And that would definitely help the walking situation as well. Yeah. So definitely more development to be done. But she's mobile, she's running, and that makes me very happy. So, Charlotte is finally off the lab table, and good thing, too. I have a lot more planned for this project, including a reinforcement learning-driven control paradigm that I'm actively developing the theory on. I'm also hoping to investigate options for network communication that will enable long-range teleoperation of the robot. There will probably be some small behind-the-scenes adjustments to Charlotte to get Mark 1, that's just the locomotion platform, ready for purchase on dragline.tech, so that you, yes, you, can start running your own experiments and adding your own hardware. This is what Dragline Dynamics will be about, doing extensive research to make effective, yet inexpensive products that give people abilities they previously lacked. Inventions should become available as soon as they are useful, but the development never stops. This you can count on me for. And you can also count on me to be back on YouTube in 2 weeks when we shift gears for a bit to a new project, or rather perfecting an old one. That's next time. Stay amazing.